Let's now go beyond simple naive averaging and incorporate the size of the population of the reviewers. And this will lead to what we call Bayesian ranking. But before we can go there, we first have to look at what's called Bayesian estimation, named after the mathematician Bayes, whose work was then further extended by the famous mathematician Laplace. And Laplace raised a very interesting question. What's the chance that the sun will rise tomorrow if you have observed that it has been rising every morning in the past, say, 100 million days? Now, you may think this is a funny question, but for now, ignore the fact that you know something about the underlying physics of why the sun rises. Now, purely view this as a question that you observe something. It has been coming up every morning in the last 100 million days, and then what's the chance you predict that it will come up again tomorrow? Can you say, well, it can be exactly 100%. Mathematically, again, we're not talking about the underlying physics, but this is such an overwhelming number. So what should it be? And this is an interesting thought experiment that we can simplify a little further to say, suppose I give you a sequence of n experiment, and I say S out of n experiment, for S smaller than n, I observe 1. Okay, and I ask you the question, what's the chance the next experiment also return 1? Now, without going through the foundation of probability theory, intuitively the answer is just S over n. Because in the past, S out of n chances runs gave us this result of 1 as well, our observation. So call this question number 1. Suppose now I switch to another question and say that also run n experiments, and the experiment is actually that there is a coin that's loaded and I flip it. If it's heads, then I return 1. If it's tail, then I return 0. And again, as out of the last n runs, I observe 1. I ask the question, what's the chance the next time you will also see 1? You may say, hold on, isn't this question the same as the last question? Shouldn't the answer also be S over n? Well, not according to the Bayesian view of probability. The Bayesian view is a very powerful and for some time a controversial view in probability theory community. But what it says is that now that I've given you some prior information that the experiment consists of flipping a loaded coin, then you'll be able to make some model about that based on the observation in the last n rounds. And therefore your answer may be different. What is that answer? Let's derive that in the next 5 minutes. And then we'll come back to answer this question. Why is it different from S over n again? The essence of the Bayesian view, the philosophical underpinning, is captured in this picture. You got underlying model. Later in the course, we'll also see different kind of latent factor model. We'll see hidden model. We'll see reverse engineering of network topology as well as protocols. Philosophically, they follow a similar spirit. In this simple question, the underlying model is just captured by a parameter p. That's the chance that a single coin flip of this loaded coin will result in a head, and therefore observation of 1. Now, different p's will clearly lead to different observations. That goes without saying. But the Bayesian view also says different observation is telling me something about the p. And more observation I have, the better I can build a model for p, from which I can then do forward engineering to predict the future outcome. You first reverse engineer the p before you make prediction. So in our case, we say that if you know the value of p, then we know that the chance of seeing S out of n flips heads is simply a binomial distribution. It is p to the power s because you observed s such cases, 1 minus p to the power n minus s because you observed n minus 1 of such cases, and there are n choose s possible combinatorial arrangements of that. sequence of S out of n being ones. So this is just a binomial distribution, and we all know that for a fixed P. What is now flipping our heads around and turning the table is that since that's the case, then the probability distribution of P, let's call that f of P, should be proportional to this observation frequency. If we count the frequency in the observation of heads, then that would tell us something about the underlying probability distribution of this value of P. And let's just pause for 1 second, because it sounds intuitive. It's actually quite counterintuitive at first sight. Because we're not saying that let's go ahead and predict. We're saying that let's build a model of P, and that model says that P's distribution should be proportional to our observation. This proportionality principle is what Laplace did to extend Bayes' understanding of the relationship between observation and model. And I say it's proportional because the self is not a distribution. We have to normalize it by integrating over all the possible p's, and dp there, p can range from 0 to 1. And now this is indeed a probability distribution. And as a function of p, that's the probability distribution f of p. So all we need to do now is to evaluate this integral and then do the division, skipping those detailed steps, because that's not what we care about in this course. We get the following answer. It's m plus 1 factorial over s factorial n minus s factorial times p to the s n minus 1 minus p to the n minus s. Okay, so that is the probability distribution of p as a function of n and s, as a function of how many runs have you carried out and what is the number of ones that you have observed. And now we're basically done, because we know the conditional probability of observing another one given a particular p-value is just p, right? Because we know what p is, so condition on that, the chance that we're getting a conflict of heads is just p. So we have to unconditionalize it by integrating this answer p across the probability distribution f of p for p from 0 to 1. And substituting that complicated looking expression for f of p and doing the integral again, skipping the steps from integral tables, the answer is remarkable and remarkably simple. It's s plus 1 over n plus 2. Let's recap. We started by saying that you want to make prediction, right? But hold on first. You know something about the model. So based on your observation, first build the model around p. And that's how we get to the distribution of p. Then you make prediction. And the answer is s plus 1 over n plus 2, which is clearly not s over n. So mathematically, you know this is the right answer if you follow Bayesian analysis. But intuitively, why not s over n? Well, here's one way to intuitively make yourself feel comfortable. The moment I tell you this prior information about the model, it's as if I've told you that I've run for free 2 trials. One trial shows up heads, one trial shows up a tail. So when you tally, you should say it's n plus 2 trials, and the number of heads I've observed is s plus 1. Okay, because the impact of that prior knowledge about the underlying model is, roughly speaking, intuitively speaking, equivalent to as if you had free runs, 2 of them, one showing head, one showing tail. So now we can take this philosophy to understand how to do ranking of competing product of the same category on Amazon. And we know that knowing heads shows up 100 out of 103 runs is going to give us something different than observing 10 heads out of 13 runs. Similarly, on Amazon, we know that knowing there's a lot more reviewer of a product compared to its competitor should give us some information. So suppose you got a list of products indexed by I. For each product I, there are n sub I reviews, and the average, simple naive average, is R sub I. Okay. Then we say, look across all of these products in the same category. You can add up the NIs, call that total number of review for all the products in the category, big N. And then you can look at the reviews, summation of NIRI, okay, divided by big N. That is the average, total naive average across all product category, call that big R. So if I know a certain product I got a lot of review NI relative to big R, I should put more trust to the corresponding RI. Whereas if there's very few reviews NI relative to R, then relative to N, I'm sorry, very small NI relative to N, then I would rather put the trust on the average review. It's like saying that if this product got a lot of reviews, I should trust its own average. But if it got too few reviews relative to N, then I should pretend as if it is an average product across the entire category. And it turns out that the Bayesian adjusted value RI 2D follows the following expression. It is NR, which is really is the summation of NI-RI, plus NI-RI divided by N plus NI. So we can view this as a sliding ruler. On the one end is your product I's own average review, RI. On the other end is the total average across all products in the category. And we say that the actual RI2D, the Bayesian adjusted rating average, is somewhere between the naive average of your own product and the total product, depending on how much I can trust this RI. If this RI has a lot of NI backing it up, I'll move closer to RI. If it's got very few of them, then I'll just say, you know what, I think I would rather not trust this RI that much and more towards big R, the average rating for all the products. So RI2D is sliding somewhere in between and is sliding according to this formula. Let's take a look at two extreme cases. In one extreme case is this NI for a certain product is so small that we can ignore it compared to the big N. Let's say it's near zero. Let's say this is 1 and big N is 10 trillion. All right, so we can pretty much ignore this term and this term, and in that case RI2D is just R. It moves all the way to this extreme end. Or let's say NI for a certain product is N over 2. So half of all the reviews in this category goes to this particular product. So relative to the other competing products, we can say this product I got a lot of reviews. So we should be able to trust more of its rating. So if we substitute NI over equals N over 2 into this expression, what we see is that RI2D now equals 2/3 R plus 1/3 RI. So it's moving much closer to RI now. And it turns out that this formula is used exactly in Internet Movie Database, IMDb's ranking of the top 250 movies of all times based on all the ratings of these movies. It doesn't use a simple naive average because some movies got a lot more reviews and ratings than other movies. Instead, it used this Bayesian adjusted NR plus NI RI over N plus NI. the relative sample size of the review NI relative to the total across all the movies plays a role here. Here's another example, Beer Advocate. This is a website that ranks all the different kinds of beers around the world. And it used almost the same formula. Okay, each beer I's Bayesian adjusted ranking R2D equals N mean, I'll explain what this is in a minute, times R plus NIRI over N mean plus NI, where N mean is the minimum number of rating that you need in order to even show up in the top beer ranking on this website. So why use N mean instead of N, which is the total accumulated number of ratings? One reason is that if you use this big N, as time goes by, the total N will only increase and the dynamic range of R2DI will be shrinking. So Beer Advocate decided to use a twist of this formula and say, instead of looking at the total number of ratings, just look at the minimum ratings that you need in order to show up on the website. So in fact, you can pick this as N mean, or as some other kind of number that somehow corresponds to a notion of the total review population. What about Amazon then? Does Amazon use Bayesian analysis in its ranking? And what else does it use? We'll come to this in the next and the final segment of this lecture's video. But first, let me highlight two drawbacks or limitations of this Bayesian ranking. Number one, this is useful for ranking. Therefore, you must have a backdrop of a scale of all competing products' number of ratings. If you just want to do adjustment of the number of stars, say 4.5 stars from 121 reviews, you can do that. Okay. You must also know what about the competing products, how many reviews and what's the naive number of stars that they receive in order to do the adjustment, in order to lead to a ranking of the product. So that's why on Amazon's homepage, you can click through a number of links to look at the ranking, which actually incorporates Bayesian. But if you look at just number of stars, they still show you the simple naive average number. And you just have to process in your own head by incorporating the impact of number of ratings somehow according to your own notion of N. The second limitation is that this formula implicitly assumes actually a Gaussian distribution of the review scores. As we mentioned, that often they have a bipolar bimodal distribution, or in general multimodal distribution, in which case will lead to a slightly different and more complicated formula. But we will not have time to go through that set of material. So what we're going to do now is going to go through two examples on Amazon, a small and a larger example, to figure out what Amazon does and how does it use the Bayesian viewpoint to do ranking.